students. So in last class we have talked about total internal reflection, the conditions under which TIR takes place, and I have told you that the conditions are that light should be incident from a denser medium onto a rarer medium, and also that the angle of incidence should be greater than critical angle. So that is what we have seen. We have discussed few examples, and at the end we have drawn the ray diagrams to understand how TIR takes place, right. So we will see some more examples today, and eventually we will talk about few concepts like the formation of mirrors and the optical fibers and things like that. Okay. So let us consider a scenario like this. So let us take a prism. So a prism is basically a structure like this, a triangular structure, and just visualize this in this manner and brought outside. So which means if I draw a 3-dimensional view of that, it looks something like this. So this is how a prism would look like. So just like we have a cube would be a square which is just extended outwards, right. So in the same manner, prism is something which looks like a triangle. It could be any triangle. I have taken a right angled triangle, and if you just extend it outwards, so this is the kind of 3-dimensional structure that you would get, right. So if this is made up of some material, let us say any material, let us consider that the refractive index of this is some 2, clear. So we have taken a prism which is like that. So let us say that this angle here is 30 degrees and this angle is 60 degrees. So now let us take a scenario where a light ray is incident onto this prism normally. So the angle of incidence here is 90 degrees, clear. So we need to trace out that light ray. So let us see how that can be done. So in this particular scenario, we can consider that we know that because this is normal incident, the light ray just enters into the medium without undergoing any deviation, right. So I will draw it little bit down. So if this is the incident ray, so this light ray just enters into the next medium in this manner without undergoing any deviation, and it will now be incident onto the next interface. So now if you look here, so the inside medium is having a refractive index of 2 and the outside medium is air. So which means this light ray which is incident in this manner is now incident from a denser medium onto a rarer medium. So we will have to check whether TIR takes place or not. So I will draw the normal here first and look at the angle of incidence, and how much will that angle of incidence be. If this is 30, we know that this is also 90, which makes this angle 60, right. So if this is 60, this would be 30 degrees once again. So this angle would be 30 degrees. Okay. So now we need to check what happens in this scenario. To check whether TIR takes place or refraction takes place, I need to know the critical angle, correct. And you all know how to find critical angle. We know that the value of sin theta c is equal to mu of rarer medium divided by mu of denser medium, correct. So if I use that, rarer medium is 1, denser medium is 2, so which means I will get sin theta c is equal to 1 by 2, which would imply the value of theta c is equal to 30 degrees. So that is the critical angle for this particular scenario. And if you look at this particular case which I have considered, the light ray which is incident is having an angle of incidence of 30 degrees at the second surface. So what happens? So when light ray is incident at critical angle, we know that the light ray grazes along the interface. So which means this light ray which I have considered here will now graze along the interface in this manner, and it would travel in this way, clear. So this is the incident ray. So this is how the ray is incident, this is the incident ray, and it travels in this manner and eventually comes out in this manner. So this is what we can call as refracted ray. So that is what happens in this scenario. So this would be the path followed by the light ray, clear. Okay. Now let us see one more case similar to this. I will take the same prism, I will just change the orientation of the prism this time. So I will take this prism and place it on a different side. So the same prism, but it is placed in this manner. So let us consider a situation like that. So this is how the prism is, right. So which means this angle is 30 degrees, this angle is 60 degrees, and this is same 90. So the same prism is now placed with a different base. This one is now the base. Now once again the light ray is incident normally, and we will have to draw the ray diagram for how it travels. So let us consider this as case 1 and this one is case 2. Okay. So the idea is once again the same. The light ray which is incident from here will directly enter into the medium because of the normal incidence scenario. So this light ray will just enter into this medium like this, and if I draw a normal at this interface, so you can say that this is 60, this angle would be 30, which would make this angle 60 degrees. So this angle would be 60 degrees, correct? Okay. Now we once again know that the critical angle is 30 degrees and the angle of incidence in this scenario 60 degrees is greater than that. And you know what happens when incidence is greater than critical angle? TIR takes place. So this light ray will get reflected in this manner. So it gets reflected in this manner in such a way that this angle is also 60 degrees. Clear? So this is how the light ray would be. Now it comes and strikes this interface. So which means we will have to check what happens at this interface also. So to be able to do so, I need to know the angle at which this is incident, correct? Right? So let us look at the triangle which is formed over here. So we know that this angle is 30, this is also 30, and because this is 60, I can easily say that this angle here will also be, this angle will also be 30 degrees. Now if you look at this smaller triangle, 30, 30, which makes this complete angle 120 degrees. So if I draw a normal here in this manner, so what would be the angle of incidence at this surface? That would be 30 degrees once again. So this angle would be 30 degrees. So which means the light ray which is incident like this, after reflection from here, it is striking the next interface at an angle of 30 degrees. Remember, even this light ray is incident from denser onto rarer medium. So I will have to check what happens. So this angle of incidence is 30 degrees. So what happens when light ray is incident at 30 degrees, which is also the critical angle? The light ray grazes the interface, right? So what happens here is that this light ray just travels in this manner. So this is how the path of the light ray would be. Clear? So just look at the arrow marks. The lines with the arrow marks are the light rays. So this is how the light ray travels, and it eventually comes out in this manner. So here this is the incident ray, and we can say that this is how the final ray comes out. Clear? So that is how we can understand. Now let us see one more scenario. Just like we have changed the orientation from here to here, let us change it even further. So this time let us consider that the light ray is incident perpendicular to the interface. Here we have taken perpendicular to this surface. In the next case we have taken perpendicular to this surface. Now let us take the light rays incident perpendicular to this surface. So I will draw the diagram over here. So let us take this as the prism, right, and let us say the light ray is incident in this manner. So this is the incident ray and it is perpendicular to this surface. Now once again the light ray enters without any deviation, strikes the next surface, and we will have to check what happens here, correct? So if I draw the normal, you can easily tell what this angle is. Okay, this is 30, this is 60. So how much would this angle be? You can easily tell that. So 30, 90, 60, which means this angle would be 30 degrees. And once again, angle of incidence in this particular scenario is 30, which is critical angle. So at critical angle what happens? The light ray enters, or we can say that it just refracts into the next medium, making 90 degrees with the normal. So the normal is like this. So which means this light ray, after this refraction, it grazes the surface and it comes out in this manner. Clear? So that is what happens, because this angle is theta c. So it is the same concept we applied even here as well. Even here the angle of incidence is theta c, so the light ray grazed the interface. Even here the angle of incidence is 30 degrees, so it grazes the surface. Clear? So this is case 3. Actually, we can discuss one more case in the same situation, the same prism which I have drawn here. So this light ray which is incident normally, if it is incident somewhere over here, so if it is incident somewhere over here like this, it enters into the prism and it strikes this interface. So in that case what happens? That can also be understood. Let us see that also. So I will draw, we will see that case as well. So what I am saying is, this light ray is incident in this manner, it enters into this prism and strikes this surface instead of this surface. Okay, let us see that. So for that I will draw the diagram little bit bigger. So let us say this is the prism like this. So the same prism, I am just drawing it slightly bigger. So this angle is 60 degrees, this angle is 30 degrees, and this is case 4. Okay. So now once again the light ray is incident normally here, right. So if I draw that light ray, so it would be something like this, so 90 degrees, and as you can see, this after entering will strike here, strike this surface. So in this scenario we will need to check what is going to happen to that light ray. So I have drawn the normal. So let us look at the angle. So this is 60, this is 90, which means this is 30, correct. So the angle of incidence here would be 60 degrees. So that would be the angle of incidence. Now you know that theta c even in this case is also 30 degrees, but the light ray is incident at an angle of 60 degrees. So what happens in that scenario? The light ray reflects back, TIR takes place. So this light ray will get reflected back and it strikes this surface this time. So this angle will be 60 once again. Now because this light ray is striking this surface, we once again have to check what happens at that interface. So let us see. So I will draw the normal. So if you look, let me draw it slightly according to the scale, because this angle is 60 degrees, so it will be slightly wider, so something like this. So if I draw the normal here, the normal would be in this manner, correct. And now let us see what happens at this interface. So this is 60, correct. So if this is 60, I can easily say that this angle would be 30 degrees, correct. So draw the diagram clearly by yourself, you will clearly understand that. So yeah, so this is 60, this is 30. Now what happens at this surface, because the angle of incidence is 30, we know that we have seen in other cases also, the light ray should emerge in a grazing manner. So it should graze the interface. So which means after refraction here, the light ray travels like this in a grazing manner. So this would be how the final ray travels. So I will draw the arrow marks to show you how the light ray is traveling. So it enters directly, TIR takes place here, right, because angle of incidence is greater than 30 degrees, and it strikes the other surface, and here the angle of incidence is 30 degrees. So the light ray emerges in a grazing manner. So this is the final ray, and this is the initial ray. So that is what happens in this case. So we have basically discussed 4 different cases here. So I want you to do these 4 cases on your own once again, draw the ray diagrams, explaining it to yourself. So that would be more clear in that scenario, right. Students, now we will discuss an effect which is created because of total internal reflection, right. So it is something like this. Let us consider that we have water here, right. So this whole medium here is water, and let us say this is air, and you are viewing it from here. So, you are just looking through here, and let us say there is a source of light somewhere over here vertically below your line of sight. So, there is a source of light. So, let us say this is a point source of light. So, you can consider a bulb or something like that which is placed inside water, it is illuminating, right. So, it means that the light, this is sending light in all the directions. So, light comes out of it in all the directions, right. Now, this light which is coming out will get refracted through this interface and then reach your eye, correct. Okay, fine. So, now what happens in this scenario is, if I look at the light rays which are coming from this object, let us see what are all the light rays that come out. So, I'll draw some light rays. So, one light ray which is incident normally will just pass through, right. Let us take one more light ray which is incident in this manner. So, another light ray which is coming from this point source will be incident in this manner, and we can say that because of the small angle of incidence created here, it refracts away from the normal, clear, because water is denser, air is rarer. So, the light ray after refraction bends away from normal. So, this light ray bends away from normal and it goes away in this manner. So, let us draw one more light ray coming from the point source which is like this. Okay. So, now the angle of incidence is slightly larger, right. Let us consider that even this light ray is going to get reflected back, it undergoes it undergoes refraction and it just refracts into the air medium. So, similarly, if I look at another light ray, so let us say that is incident in this manner, and let us consider even this light ray is getting refracted in this manner. Now, remember, this does not happen for each and every light ray, because as you can see, as the angle of incidence is increasing, the angle of refraction is increasing even larger. So, there will be a point of time where this refracted ray will become parallel to the surface, and at what condition does it become parallel to the surface? You all know that. Let me draw that light ray as well. So, if I draw the light ray like this, so let us say this is the incident light ray, for which after refraction at this surface, the light ray becomes grazing the interface scenario. So, I am repeating once again. So, all these light rays are refracting and entering into the air medium, whereas this light ray, if you observe, for some particular angle of incidence, we know that because it is travelling from denser medium into rarer medium, we know that the angle will definitely reach 90 degrees at some scenario. So, this angle can reach 90 degrees, right. Now, what is this angle? Can you tell me, can you understand what this angle is for which the light ray becomes parallel to the interface? That would be theta c. Now, what this means is, now observe closely, can I say that all these light rays which we have drawn earlier, so here the angle of incidence is very small, here it is slightly larger, even larger, and it is theta c. So, if I go away further, what happens to the angle of incidence? Let me draw that light ray as well. So, if I draw a light ray like this which is incident in this manner over here, can I say this angle is definitely greater than theta c, right. So, if this angle is definitely greater than theta c, what happens to this incident light ray? It gets reflected back, clear, because of TIR. So, this light ray will get reflected back in this manner, and you would observe that after some particular angle, all the light rays will get reflected back. You can take any other light ray also which is incident here, even that gets reflected back. Only the light rays which are at an angle lesser than this will refract into the next medium, correct. So, only these light rays, I'll just draw the angle representing that, only these light rays which are in this region, right. So, this light ray here corresponds to, so the one which I am putting a dot. So, this is the light ray which corresponds to critical angle. So, can I say that all those light rays which are incident at an angle lesser than critical angle, which are these light rays, so in this region, so all these light rays, can I say that all these light rays will refract, whereas the light rays which are at an angle greater than this are going to get reflected back because of angle of incidence being greater than theta c. Okay. So, this is what happens. So, we have understood this. Now, is it going to just happen on this side like I have drawn in the diagram? Won't it happen on this side? It does happen on this side as well, correct? So, whatever I have drawn on that side, I can say that if I draw the diagram on this side, I am not going to draw all the light rays, I am only going to draw the theta c light ray, clear? So, this theta c light ray. So, if I draw the theta c light ray, so this is water, air, and if I draw the theta c light ray, that would be something like this, right, and this is the one which becomes parallel to the interface. So, any other light ray which is incident at an angle greater than this will reflect back. Maybe I will draw one such light ray just for understanding. If I consider this light ray which is incident here, this gets reflected back. Okay. So, this is what happens in this scenario, correct? Now, see, there is one important thing which you will once again have to consider. Remember that this is a point source of light. It is going to send light not just in two directions, correct? It is going to send light in all directions. It sends light like this, it sends light like this, like this, like this. So, light goes in all the three dimensions, correct? So, whatever I have drawn here is not just happening in the plane of the board. So, please listen to this carefully. Whatever ray diagram which I have drawn here is not just confined to this board, it happens here as well. So, a light ray which is incident at theta c will travel like this, correct? A light ray which is incident at an angle greater than theta c will get reflected back, right. So, whatever I have shown you here is happening in all the 360, I mean in all the directions. Is that clear? So, now think about that, try to visualize that scenario, that whatever diagram which I have drawn is happening in all the directions, and think about what this person would observe looking from the top. Think of it. Now, if you look at the plane which I have drawn, in this plane he will see that starting from here, because this is where the theta c light ray is coming and striking. So, this is where the theta c light ray comes, correct. So, this light ray which is making an angle of theta c, so this light ray is just going away, correct. So, can I say that in all this region, so in throughout this region, he will observe that the light rays are going to come out. So, this whole region starting from theta c on this side till theta c on this side. So, whatever light ray strikes this region, the light ray will come out, and whatever light ray strikes out of this region, you can see this region or this region, any light ray which strikes that region is going to get reflected back. So, what he would observe is that light rays are only coming out from this region. See, what I am drawing here is a line in two-dimensional view, but try to think of it in a three-dimension. So, if it is coming out in this line, and if this phenomenon is happening in all the directions, what will he observe? Think of it. So, we can say that let me draw the theta c light rays darker so that it is clearly visible for us. So, these are the theta c light rays. So, this is one theta c light ray, right, and on the other side this is the theta c light ray. Okay. So, what we would observe here is that, so there is a cone like structure which would be formed. I hope you can visualize that. So, if you look at these two lines and just turn it in all the 360 degrees. So, just try to turn these two light rays. This happens in all the directions. So, if you just turn it like this, so a cone like structure is formed, correct, and we can easily say that only those light rays which are coming from inside the cone will come out, and any light rays which are going to come from outside the cone will get reflected back. Clear? So, what this person here would see here is that there is a cone like structure here, right. So, the light rays are coming through that cone like structure, and only those light rays which are coming through that cone like structure, which would be in this circular region. So, let me draw it slightly better. So, like this. So, there is a cone like a circular cross section on the top of the interface. So, this person who is seeing from the top will see a circular region, and he will observe that light rays are coming only from inside the circular region, and from outside the circular region he will see that the light rays are basically he does not see anything, it appears darker, because all the light rays striking outside the circle will get reflected back. Remember why I have drawn a circle here, that is very important, because although till now I have explained it in this plane, this light rays are not confined to the plane, they are traveling in all the directions, they are traveling like this, like this, like this, like this. So, only those at angle lesser than theta c will be inside the cone, and only those light rays will come through this circle. I hope this is clear, right. So, we can say that this circle is the region from which this person observes light coming out. So, this is the circle from which light comes out. So, we can say that that is basically called the circle of illumination. Circle of illumination. Clear? So, they will generally be asking you questions like this: what is the radius of that circle, or how much area through which the light comes out according to that person, and questions like that. Clear? So, I hope the concept is clear. We will solve that mathematical analysis, we will do the mathematical analysis also, but first keep in mind what is happening in this scenario. Why is this person able to see that light is coming only through this circle and not from the other side? And the reason is because light striking at other regions outside this circle will have a greater angle of incidence, greater than theta c. So, they will just get reflected back and they will go back into the water medium once again. I am just taking water for understanding, it could be any denser medium which is transparent. So, that is the basic idea, right. So, we can say that this area, let me not make this even, let it be simple like this. So, I hope you are getting this, right. So, just try to visualize a cone with this angle with the vertical being theta c. So, any light ray coming from inside the cone and striking the interface will refract, will enter into air, and any light ray which is coming from outside the cone and striking the interface will get reflected back. Is that clear? So, that is what happens in this case. So, let us try to find out, as I told you, the radius of that circle of illumination. So, we need to now find the radius, and as you can see, I'll take this triangle on this side because this side is little bit bulky. So, I'll look at this triangle. We know that the light comes from inside the triangle. The lines which I have drawn in dark is the cone through which the light comes out, right. So, now look at this triangle which is formed. Maybe I'll name the points. So, let us say this is S, A, O, and this is B. Clear? So, I will maybe draw the cone here. So, the cone would be something like this. So, only those light rays coming from inside the cone will come out in this manner. Clear? And light rays which are coming from outside the cone will get reflected back. So, even on this side they get reflected back. So, this is how the interface would be. So, this is what generally happens, and the person would see that this region, this circular region which is formed over here. So, this circular region is brighter because that is the region through which light is coming out, even this normal ray as well. So, all these light rays will only come out from inside this circular region. So, we are trying to find out the radius of that circle. So, this is theta c, and if you look at the triangle AOS, clear. So, this angle is theta c. Let us consider that the depth at which the source is placed is some h or d, it could be, you can take it anyway. So, let us consider that the depth of source is d, clear. Okay. So, now we know this length, we need to find this length, correct. So, now look at the triangle AOS. Can I say that this is theta c So, this is opposite, this is adjacent. So, tan theta c is equal to opposite by adjacent, clear. So, I can write tan theta c is equal to opposite is radius, adjacent is depth. So, radius by depth. So, from this I will directly get the value of radius as d tan theta c. So, that would be the expression for radius of the circle of illumination, clear. And if you want to write this, instead of giving you the value of theta c, as I told you in many other earlier cases, they will not give you theta c generally, they will give you the refractive indices. So, if let us say this medium is air and this is water having a refractive index of mu, you know what is the value of critical angle. How do we know that? We know that the value of sin theta c is equal to 1 by mu, correct. Sin theta c is 1 by mu. So, using this result we can find this. Let us do that. So, if sin theta c is 1 by mu, let me make a triangle. So, if this is theta, so opposite and this is hypotenuse. So, this is 1, this is mu, correct. So, if this is 1 and this is mu, I can directly say that this will be root over mu square minus 1, right. So, now what is tan theta c or tan theta in this case? Opposite by adjacent, which is 1 by root over mu square minus 1. So, we can substitute that also and we can write the expression as d. So, d divided by tan theta c. So, tan theta c would be 1 by root over mu square minus 1. So, this would be the final expression for the radius of illumination, clear, radius of circle of illumination. So, they can also ask you what is the area of the area through which the light is coming out, clear. So, you can directly find out the area of the circle, which is pi r square. So, these are the two things that they can ask you here. Students, we will see one more question now. So, if you see here, they are asking us to find the values of mu being the refractive index of this medium. So, this is a cube basically. So, find the refractive index of that medium for which any light ray incident on the surface AB, which is this, undergoes total internal reflection at surface BC. So, which means if I let us say take a light ray which is incident from here. So, whether I take a light ray which is incident like this or a light ray which is incident like this, or you can even consider a light ray which is incident like this. So, you can take any light ray basically. So, let us draw few light rays in this manner. So, okay. So, I have taken multiple light rays. So, any light ray which is incident on surface AB undergoes total internal reflection at surface BC. So, which means any of these light rays after entering into this medium should definitely get reflected from BC. So, for that to happen, we need to find the values of mu, which is the refractive index of this particular medium. So, do not worry about this light ray, this is just going to pass through, it will not even touch the surface BC. So, talk about the other rays, we will talk about the other rays, clear. So, you can consider that the cube is sufficiently large, so that any light ray which enters, if the cube is sufficiently large, it will, even if the angle is very small like this, even if the light ray enters at a very small angle. So, if the cube is very large, it will go and strike the surface BC, correct. So, let us consider a scenario like that. Okay. So, now we need to find out a condition for mu. So, we need to find out a condition for mu for which any of these light rays is going to get reflected at this surface. Okay. So, let us see what we can do in this scenario. So, what I will do is I will just draw a refracted ray like this. So, let us say the light ray enters into this medium, light ray enters into this medium at some angle r, clear. So, now it strikes this surface. Now, we know that if this angle is r, this angle here will be 90 minus r, correct. So, now what we need to do is we need to write a condition that this light ray has to undergo TIR at the surface, which means this light ray should get reflected back in this manner. So TIR should happen here. So now you all know how or what is the condition for TIR to take place. What is that? The angle of incidence, which is 90 minus r here, should be greater than theta c, correct? So that is the condition which we will have to write. Okay. So now let us observe this particular scenario and decide how to write the condition. So if I have to choose a value of mu, let us say I have taken one particular value of mu and I have taken any light ray, let us say this is light ray A, B, C, D, and let us say this is the grazing light ray, which is the 90-degree light ray. So this one here is the grazing light ray, grazing incidence scenario. Okay, so we have many such light rays. Now we will have to decide out of all these light rays, each and every light ray after entering into this medium and striking this particular surface should reflect back. Now let us think which of these light rays has the minimum possibility to get reflected back. That is what we are going to look for. So what I am going to see is, so I will take few light rays here A, B, C, D and this grazing incidence case, and I will see which of these incident rays has the least tendency to reflect here, to undergo a total internal reflection there. How do we do that? Now we know that for TIR to take place, this angle should be greater than theta c. For TIR, we can say for TIR, in that particular case 90 minus r should be greater than theta c. So this is the condition, correct? Now can I say that out of all these rays, the light ray which has the least tendency to get reflected back is the one which makes the least angle here? Think once again. See, for example, let us say we have an interface, clear? So we have an interface like this, and let us say this is denser and this is rarer, and let us consider that the critical angle for this surface is 42 degrees, right, some 42 degrees. Now if multiple light rays are incident, let us say one light ray is incident like this, one light ray is incident like this, one light ray is incident like this, one light ray is incident like this. So let me call them as rays 1, 2, 3 and 4. Now I am not giving you any angles of incidence here, I am just going to ask you which of these 4 light rays has the least tendency to get reflected back. I mean, which of these 4 light rays has the smallest possibility to undergo TIR? Let me write it down also. Which of the 4 cases can easily undergo TIR? So can you think about that? Out of these 4 light rays which are incident at this interface, 1, 2, 3 and 4, which one has the most possibility to undergo TIR? You know that higher the angle of incidence, the chances of TIR happening are more, correct? So which means, can I say that this is the light ray which I can say for sure that it will definitely undergo TIR, right? Out of all these 4 rays, I can say for sure that if at all there is any light ray which will undergo TIR, that would be this. And which has the least tendency to undergo TIR? This one, because it is making a small angle with the normal, correct? So which means if the angle of incidence is smaller, the chances are this small angle might be lesser than the critical angle. I hope you are getting this. If the angle of incidence is lesser than the critical angle, then TIR won't take place. Yes. So which means out of these 4 rays, this has the highest tendency to undergo TIR and this one has least chances to undergo TIR. I don't even have to give you this value. Let us say the value is also not given to us. I am just giving you a scenario like this, clear? So 4 light rays, which of these 4 light rays has the highest tendency to undergo TIR and which one has the least tendency to undergo TIR. You can say that the one with the smallest angle will try to refract, the one with the largest angle will try to reflect, TIR can take place. So, that is the basic idea, correct. Now, I am going to use that concept here. Now, what I am going to do is, please observe carefully, out of all these light rays, I am going to choose one particular ray which has the least tendency to undergo TIR here, clear. Let us decide which one of that will be, clear. So, I will choose that light ray which has the least tendency and I will write the condition for TIR to happen for that particular light ray, clear. I'll maybe once again tell you with this particular example, please look carefully here. In this particular case, can I say if ray 1 can undergo TIR, then all the light rays, all the 4 rays will undergo TIR. Is this statement clear? So, please I will repeat this once again, please observe carefully. So, in this particular scenario we have 4 light rays of different angle of incidence. What I am saying is that if this first light ray which has the least angle of incidence, so if that light ray is undergoing TIR, then 2 will undergo TIR, 3 will undergo TIR and 4 will also undergo TIR. Is that correct? Yes, because if this angle is greater than theta c, whatever that theta c is, so if this angle of incidence I is greater than theta c, then all of these are having even greater angle of incidence, correct. So, which means all of these will definitely undergo TIR. So, that is exactly the concept I am going to use here. So, what I am going to see here is, I will see which of these 4 or infinite number of light rays by the time it reaches here makes the smallest angle of incidence. I will check that. So, the light ray which makes the smallest angle here, if that light ray gets reflected back, can you say that each and every other light ray will reflect back? I am just using that concept. So, please try to correlate these two. What I am trying to do now is find the light ray which makes the smallest angle of incidence here and make sure that is getting reflected. If I make sure that that light ray is getting reflected, every other light ray will definitely get reflected. So, that is the concept. So, maybe I will write the condition in this manner. If the light ray incident at the smallest angle of incidence on surface BC undergoes TIR, then every other light ray also undergoes TIR. So, even though the question asks find the values of mu for which any light ray incident on the surface undergoes TIR, correct. So, what I am doing here is I am not going to write the condition for every incident light ray, I am only going to write the condition for one light ray such that if that light ray is getting reflected back, every other light ray will get reflected back. Is that clear? So, in this case if this one is getting reflected back, definitely 2, 3, 4 will get reflected back. So, same concept, clear? Okay. So, now let us see which light ray makes the smallest angle here. Can you guess out of these many light rays, which light ray is going to make the smallest angle here? So, the idea is like this. If this angle is the smallest, then this angle is the highest, correct? Because you can just extend this, this is always 90. So, for this angle to be the smallest, this angle has to be the highest. Now, we know that here there is refraction taking place at this surface, refraction is taking place, and if this angle has to be highest, then what can we say about the angle here? That also has to be the highest. I hope this is clear. I will repeat once again. We need to look for the smallest angle here. If the angle here is small, the angle here has to be large, and if the angle here is larger, it means the angle of incidence should also be larger. And what is the largest possible angle of incidence? Grazing incidence. Is that clear? So, I'll erase all the other light rays and I'll just consider only the grazing incidence light ray. So, that is what we are going to write the condition for. So, if that grazing incidence light ray is going to get reflected back, so this one. So, if the light ray which is incident in a grazing manner, which is at 90 degrees, so if that light ray can get reflected back, any other light ray will definitely get reflected back. So, that is the idea. So, this is incident in a grazing manner, this angle is 90, and we all know, we have already earlier discussed, if light ray is incident in a grazing manner, it enters into the denser medium at what angle? At theta c, correct? So, theta c will be the angle at which it enters into the denser medium. Now, if this angle is theta c, what will this angle be? We can say that this angle will be 90 minus theta c. So, that would be the idea. So, that is what we get by solving this. So, I will repeat once again, please observe carefully. So, what we are looking for is, I am making this angle the largest. If this angle is the largest, this angle is also largest, and if this is largest, this is the smallest, correct? Now, once I got the smallest angle, if I write the condition that the smallest angle of incidence scenario undergoes TIR, then every other scenario will also undergo TIR, clear? So, now the condition is pretty simple for us to write now. So, the angle of incidence here is 90 minus theta c. How do we write the condition for TIR? This one, right? The angle of incidence should be greater than critical angle. So, the condition would be, so I will write it down here. So, condition is something like this. So, this angle of incidence 90 minus theta c should be greater than the critical angle, and what is critical angle? Theta c. So, that would be the condition. So, if I simplify this, I will get theta c should be lesser than 45 degrees, right? And you all know how to write the value of theta c. We can write, or if I take sine on both sides, I will be getting sine theta c should be lesser than 1 by root 2. And how do we write the value of sine theta c? Sine theta c is nothing but mu of rarer by mu of denser, and if I simplify that, mu of rarer is 1, mu of denser is mu. So, I can get 1 by mu should be lesser than 1 by root 2, 1 by root 2, correct? And if I simplify this inequality, so I can write this as mu. Here, if 1 by mu is less than 1 by root 2, it will imply that mu is greater than root 2. So, that will be the final answer. So, please observe this carefully. So, this is a very important concept as well. So, the idea is pretty simple. This is the concept which we have used. So, which is, if the light ray with the smallest incidence can undergo TIR, every other light ray will undergo TIR. So, we found the smallest incident light ray and we wrote the condition for only the smallest incident light ray. So, that is what I have written here. If the light ray incident at the smallest angle of incidence can undergo TIR, then every other light ray will also undergo TIR, clear? So, please observe this once again carefully. So, students, now we will see the applications of TIR in real life scenario. The first one we will be talking about is an optical fiber. So, you might have heard about this optical fiber. So, generally all the internet that you get these days is through optical fibers, and many other communications also happen through optical fibers. So, optical fiber is basically a transparent medium like this. So, it is, you can consider it to be a cylindrical kind of structure, right. So, it would be like this, it is a transparent medium, and this will generally have a higher refractive index, higher mu, and what happens is that they would coat this optical fiber with some material. So, I will draw it like this. So, around this there would be a material of lesser refractive index. So, on the outside of that optical fiber we call it as cladding. So, that cladding has lesser refractive index. Okay. So, now what happens here is that, for example, let us first understand how light behaves when incident on the optical fiber. So, let us say if light is incident on this optical fiber at some angle. So, if this is a light ray which is incident at some angle I. So, we can say that because this is denser medium and surrounding here it is air. So, the light ray will definitely enter into the denser medium, right. So, if this is the normal, so it light ray enters here and it strikes this interface, right. Now, if I draw a normal here, as I told you, this medium has higher refractive index and the surrounding medium has lesser refractive index. Now, what happens here is that if the angle of incidence in this scenario, if the angle of incidence which I have taken here is in such a way that here the angle of incidence is greater than theta c. I will repeat once again. See, if this angle here is, let us say, some I dash, and let us say for this interface, the interface between the material of the optical fiber and the cladding, whatever the refractive index is, can I say that that interface will have some critical angle, right. So, if let us say the critical angle for this interface is some theta c. Now, you know that this angle I dash can be adjusted by changing the value of I, correct. So, if I increase the value of I dash decreases. We have seen in the earlier example also. If I decrease the value of I dash increases. So, I can now, what I can do is, so this light ray which is incident from here, if I make sure that it undergoes TIR at this interface, if it undergoes TIR here, we can say that this light ray gets reflected back in this manner, right. And if I draw one more normal here, if this angle is I, because of reflection, this side I dash. So, if this angle is I dash, this will also be I dash, which will mean that here this angle will also be I dash. So, what that means is that if I send a light ray into this optical fiber at a particular angle such that it undergoes TIR here, then it also undergoes TIR here, because whatever is the incidence here, same is the incidence here, correct. Because this is vertical, and this light ray is just cutting them. So, we can say that if this is I dash, this will also be I dash. So, which means if TIR takes place here, it takes place here as well. If it takes place here, we can once again use the same concept and say that it takes place here as well, and that keeps continuing. So, which means if I make sure that the light ray is undergoing TIR at one particular position, I have ensured that TIR takes place throughout the length of that fiber. And you know that whenever total internal reflection takes place, the 100% of the light will get reflected back. Clear? There is no loss of energy to the surrounding medium, there is no refraction occurring. So, that is the reason why we call it as total internal reflection. We understood that 100% of the light gets reflected back, correct. So, that is what happens in this scenario. So, this light ray will travel like this, and you can see that we are just propagating that light ray through the fiber. So, it will be propagating through reflections, and whatever is the light which you are sending from this side will eventually will be received on the other side, right. So, you can receive it on the other side. So, this is what happens. We will be using the same concept in communication purposes. Now, you can ask, how can we communicate through light, right. So, what I have explained you, whatever I have shown you here, all of this involves light, and I am telling you that this optical fiber can be used for communication. And how is that going to work out? How can we communicate through light, right? Now, keep in mind that even though I have told you that this is light, remember that light is an electromagnetic wave, and every electromagnetic wave will have the same property, yes or no? Not just light. Light is not anything which is special. So, light is just a part of the electromagnetic spectrum, correct? So, X-rays behave in the same manner, radio waves behave in the same manner, any other rays, ultraviolet rays behaves in the same manner. So, each and every electromagnetic wave will have the same property, clear? So, everything will have this property. So, if light can get reflected, if it can undergo TIR, if it can propagate through the optical fiber, through total internal reflections, any other light ray can also, any other electromagnetic wave can also undergo the same process, clear? Now, what we do here for communication is that, for example, let us say I need to propagate my sound, whatever sound I am making here, whatever speech I am telling you, my speech audio which you are hearing, let us understand how it is propagated. So, whatever noise that I am making here, whatever fluctuations in sound that I am making here, what happens is that we will first take that sound and we will feed it into a particular device. You will learn about this particular device later on in a chapter called communication systems, and the role of this device, we call it as a transducer. So, it is called as a transducer. So, what this device does is, it converts this sound into an electrical signal. So, it converts it into an electrical signal. So, it basically converts it into a wave. So, that is what this device does. So, it converts it into a wave, and what we do now is, we take that wave which carries the information regarding the sound I am producing, and we will overlap it onto another wave and we will send it through the optical fiber. So, that is how communication generally occurs, be it sound, be it light or any other kind. So, all the video or the audio which you see or any other kind of information can be propagated through optical fiber, clear. So, as you can see, it is just propagating through reflections throughout the length of that fiber. So, that is the basic idea. And once again, this earlier question which we have discussed, if you remember that, so we have derived the value of mu as greater than root 2, you remember that? So, that can also be, that concept can also be brought in this particular scenario. What I am trying to say is, they can ask you, they will give you an optical fiber like this, and they will ask you, find out what should be the refractive index of the optical fiber such that any light ray which is incident on the optical fiber propagates through the optical fiber. I will write down the question. Find the values of refractive index of optical fiber such that any light ray or any ray incident on one side propagates through the fiber, So, this is exactly same as asking the earlier question. So, in the earlier question I told you, I have taken a cube like this and light ray was incident in this manner, and I have asked you find out the values of mu of this medium such that any light ray which is incident over here gets reflected back, correct? And we have derived the result for that to be greater than root 2, considering that the surrounding medium is air. the outside medium is air. So, the same concept can be applied here. If I just consider that this is an optical fiber without any cladding, just exposed to air. So, this medium has refractive index of mu and the surrounding medium is air. So, in that scenario, I can say that which light ray has the least probability to propagate through. You can see if a light ray is incident like this, it just goes away, there is no one stopping it, and even if the light ray is incident slightly like this, we can say that it strikes at a larger angle of incidence, so it can easily propagate. So, the light ray which has the least probability to propagate is the one which is incident in a grazing manner. So, if the light ray is incident like this, so it enters at theta c, and that is the light ray which is difficult to propagate. Now, this condition ensures that even that light ray can propagate. So, that is the basic idea about an optical fiber. So, we can send electromagnetic waves through a transparent medium, through a transparent medium, just by using the concept of total internal reflection. So, we will have to make some adjustments for the refractive index of the material which we are using to ensure that all the information is propagated. Any information incident at any angle, for that to get propagated, then this is the condition that should be satisfied. Clear? Students, now let us understand the formation of a mirage. So, mirage is something which you would have observed as well. So, when you go out on a hot day and when you look far away, you would observe that there is something like a water kind of structure present somewhere, right. You would feel that something is getting reflected from there, but when you go near it, there would be nothing there, right. So, that idea of reflection which we perceive, so that concept is what we call as a mirage. So, we can explain that idea by using TIR and how and why that happens, clear. So, let us see that. So, generally when we consider this as the surface of earth, and let us say there is an object which is over here, a building let us consider. So, this is a building, and let us say this is summer, hot day. So, what happens during summers is that the ground gets heated up generally fast, and as a result of that, the air which is very close to ground will have high temperature, and as a result of high temperature, the density of air will also be lesser. So, as you go up from the surface of earth, the temperature would be decreasing. So, as I go up with altitude, we can say that the temperature decreases. Now, what happens because of this is that, so we have, let us say we have one layer of air over here at one particular temperature, another layer of air over here at slightly lesser temperature, another layer of air with slightly lesser temperature, and so on. So, what we can understand them here as different media because of them having different temperatures and different densities. So, they will also have different refractive indices, clear. So, the one with higher temperature will also have the less refractive index, less mu, and as I go up, the value of mu increases. So, I will write that down over here. As I go up, the value of mu increases. So, this is what happens, and this variation will be larger in summer generally, because the temperature variation will also be larger during summer. So, the variation in mu will also be larger during summer. So, what happens in this scenario is, because each layer has different refractive index, we can consider them as, let us say we can consider this much thickness as one medium, this much thickness as another medium, this thickness as another medium, and this thickness as medium, another medium. So, we can divide that region into many mediums of slightly different refractive index, and as you can see here, refractive index is lowest at the bottom, and as I go up, refractive index increases. Now, what happens in this scenario is, let us say there is a light ray which is starting from here and which is striking this surface, right. So, in this particular scenario, what we would observe is that if this light ray undergoes refraction, and because when compared with this medium has slightly lesser refractive index, this light ray slightly bends away from normal, and this light ray is once again incident on a medium of lower refractive index. Remember that this is the rarer medium and this is the denser medium, right, because mu is increasing in this direction. So, every medium above is denser when compared to the medium below. So, what happens here is this light ray is travelling from denser into rarer, correct. So, it goes away from normal. So, even here you can say that the light ray slightly bends away from normal once again, clear. And if you once again observe here, the light ray bends slightly away from normal further, and this phenomena keeps happening. And you can consider this happens once again, the light ray bends even further away from normal. So, the angle will be continuously increasing with the normal, and there will be one point of time where this angle of incidence may become greater than the refractive index, I mean the critical angle of this particular interface. So, what happens if this angle of incidence becomes greater than the critical angle of this interface? The light ray gets reflected back, total internal reflection will take place. So, this light ray will get reflected back, and whatever has happened here will once again repeat on the other side. So, it travels like this, again like this, again like this, and eventually it travels and it comes out of this medium in the exact same manner. Whatever has happened on this side, we can consider that the same thing will happen like this, and the light ray comes out, clear. So, what you can see here is that there is no reflecting surface over here because of the variation in mu that was created because of the temperature difference. We can observe that the light ray is actually bending and it has turned back onto the upper side, clear. It was initially travelling like this, it is undergoing multiple refractions, and at one point it has undergone reflection and it has turned back and travelled in this manner. So, it is finally coming out in this manner. So, for example, let us say there is a person who is standing over here, and if he is receiving a light ray from here, let us say he is receiving the light ray like this, what will he think? He will think that the light ray is coming, he will just extend the light ray backwards, and he will think that the light ray is coming from somewhere over here, whereas that light ray has actually originated from here and it has travelled all this way around in this manner. See, one important thing which you will have to keep in mind is that this one, even though I have drawn it as straight lines, one straight line, another straight line, straight line, straight line, straight line. So, that is not exactly how it occurs, because the variation in refractive index is so small, and these medium will have small thickness, clear. So, the moment it slightly bends, it will go to a different refractive index. Again it slightly bends, it goes to a different refractive index. So, this light ray is undergoing refraction continuously, and at one point it is getting reflected and it travels in this manner. So, what generally occurs is that this light ray which is incident would be in the form of a curve like this, and it reaches this person, clear. And the reason why it is travelling in a curve is because of continuous refractions that are happening through different media, clear. So, this person, what will he think? He will think that the light ray is coming from here. So, he thinks that there is something which is over here. Now, what makes a person think that there is something behind or beneath earth? He will think that if something is inside, if something is formed over here, that can happen only if there is a mirror here. So, if there is some sort of a mirror here, so mirror like reflecting surface, so then that mirror will create the image of this object over here. So, that is what that person thinks, correct. So, that is what he will feel or we will feel when we go out on a summer day, that there is some sort of a reflecting surface at a far away distance, because light which is travelling from here, it is bending, and by the time it is reaching your eye, you will think that the light ray is coming from somewhere over here, and you will think that there is some sort of a reflecting surface, and this kind of idea is what we call as the formation of mirage. So, this image which is formed here, so this is what we call as the mirage, clear. So, this we can say that it occurs because of the total internal reflection that is occurring at this surface, clear. So, that is the basic idea. So, with that we will be ending the concept of total internal reflection, right, and in next class we will discuss about prisms.